Now, before we answer this question as to what the reason is, let's go back, take your inspires, and I'm going to add another page here, another graph page. You can add a new problem if you wish. I'm just going to add a new page. And I want to put in the function. What was my function again? X minus 6 to the 2/3 power. Okay. So, okay, and that's going to be to the 2/3 power. I'm going to get a really interesting graph out of that. I'm just going to pull that screen over so we can see it a little better. Okay. What are we going for in this problem? It says, find the derivative if it exists. According to our analytical work, we would say it does not exist because we get a zero denominator. Now, a lot of times that represents what on a graph? Sometimes, but a hole is when we're able to remove the problem, and then we get a hole. Not going to get a horizontal line from this. An asymptote. Which one, vertical or horizontal? Usually we get a vertical asymptote out of this, but it doesn't look like there's a vertical asymptote there. In fact, let's talk about it. Is the point where the input is 6, does that point exist? I think we did that already, didn't we? Maybe not? Oh yeah, there we did, right there. 6. If we put 6 in there, we get a point. So let's go ahead, let's put a point on here. And I'm going to put a point anywhere that I want and change that coordinate to be 6. And sure enough, there it is. Something's wrong, though. Something's not happening here. So let's take a look. Remember, a limit exists if what happens on either side? The one-side limits have to be what? Same value. Let's take a look at this. Go in and put another couple points on this curve. Put one on one side of 6, less than 6, and put one on the other side. They don't have to be at the same input values. Just put a point there. The limit that we are finding over here is determining slope of what? This whole limit is determining slope of what? The derivative. Not the slope of the derivative. Find the slope of the tangent line. Okay? So let's take a look at, go into menu, go down to points and lines, and pick up a tangent. And let's put a tangent at both of those places. I'm going to grab the ends of those so I can extend them a little bit so I can see them. There we go. What about these tangent lines am I interested in? Well, what's the derivative tell us? The derivative is interested and gives us what? Slope of the tangent line. So what of these tangent lines am I interested in? Thank you. Say it a little bit louder. Slope, yes. Isn't that what a derivative is? The slope of a tangent line? We've got the tangent lines. What's the slope of each of these? Menu, measurement, slope. Let's find the slopes of each of these. There we go. You can, label those as slopes if you want. I'm not going to do that for us right now. But suffice it to say that I've got the slopes of those tangent lines. You just told me that the limits do not exist if I come from both directions and I don't get to the same value. The derivative is telling me the slopes of these tangent lines. Let's see what happens here. If you're with me on this, grab one of those tangent lines and bring it down close to 6, the 0.60. The one that's less than, on the side less than 6, what's the slope going toward? Seems to be -1. Whoops. Wow, did you see what happened there? I'm going to leave it right there. Negative, right? Negative. Take the other point on the other side. Bring it also close to that point. Look at the slope. What's the slope going to? Excuse me? So the one on the less than 6 side has a slope that is what? Say it louder. Say the first word only. Negative. Negative, whatever. What about on the right side? Positive 1. Is there any way for a negative quantity and a positive quantity to meet? No. They're not going to the same place. So, tell me, why does the limit not exist over here? Two different one-sided limits. Yeah. I'm going to give you another word to use instead. We call this point here, we call this a cusp. It's spelled C-U-S-P. See you later. Bye-bye. It means that there's a sharp point in the curve. That what happens with those tangents is that the slopes do not converge. They go down, and one's going to negative, and it's like going to negative infinity and going to positive infinity. It's that type of thing. And when we are looking at dividing by 0, remember dividing by 0 also means that they're going to infinity. Okay? So, if you want to use the word sharp point, you may do that. Okay. So, does the derivative exist? And the answer is no. Now, you can do all the drawing and all that stuff, but I really want to see your work. And this, again, let me go back and ask this. Does this function have a derivative that exists anywhere? Are there any derivatives that exist for this function? Where? Everywhere except. Okay? And that's why the problem said, look only at the point x equals 6. Because the person who wrote the problem knew that was going to be a problem point. Okay? The derivative is every place except at that. Okay, let's go on. Well, this should be easy enough then. Oh, we didn't ask that question. We better go back and ask it. Is this function continuous? Now, do not confuse. Don't confuse the continuity statement. First of all, does the point f of 6 exist? Is it defined? Yes. Is the limit as x approaches 6, does that limit exist? Careful. Yeah. We're talking about the limit of the function here, not the limit of the derivative. Ah, yeah, big difference there. Okay? We're not looking at the limit of the slopes of those tangent lines. We're looking at the limit of the outputs of this function. Does the function have outputs as you get closer and closer to 6? And are they one and the same? And the answer is yes. Is the output value the same as the limit of the function at that point? And the answer is yes. Is the function continuous then? Yes. Okay. Was the function differential? Was there a derivative there? No. Here's a statement. Is it possible for a function to be continuous at a point but not differentiable at the point? And we just saw an example. Now, someone in the last class asked me for clarification, what does the word differentiable mean? And I I kind of assume we know that, but I guess it doesn't look like derivative, but it means the same thing. Remember we talked about in that notation that the dy dx were differential y's and differential x? So we say, is it differentiable? Can we build that slope along the tangent line to tell us what the slope of the tangent is? So differentiability means, does it have a derivative at that point? So is it possible for a function to be continuous but not differentiable? And the answer to that is yes. And we looked at an example. We just got through looking at it. What was that? That was the one x minus 6 to the 2/3 power. Okay. Then the question is it possible for the function to be differentiable but not continuous? That's the other question. And let's take a look at this. If we have a function, let's say that looks something like this. Obviously not continuous, right? Is it differentiable? And the problem is you don't have a point here. So how can you have a derivative to it if you don't have a point? We also can say that we have to be approaching from both directions and get the same value, and that doesn't always hold up. But we don't have a point here, so we can't say that it is differentiable there because it's not, or that it's, you can't find a derivative if it's not continuous. So the answer to this one is no. Is it possible to be differentiable but not continuous? And the answer is no. So here's our theorem. Differentiability implies continuity. In other words, if you know the function has a derivative at a point, then you know it's continuous at that point. You don't have to do anything more. It's kind of a nice little shortcut to all of our work if we know that it has a derivative there. Okay, let's go on. Let's find the derivative, or let's find, for Eric's benefit, all of the derivatives if they exist. Okay, let's find the derivative if it exists at x equals 1. And really, when we're at a point, we would only have one derivative here. Okay, let's talk about it. It's a piecewise defined function. Okay. We know that it can be continuous and not differentiable, but let's talk about it. Is this function continuous everywhere? Well, let's see. X minus 1 quantity cubed, is that piece of the function continuous? How do you know? It's a polynomial. Absolutely, yeah. It's a polynomial function. If it's a polynomial function, polynomial functions are continuous everywhere. So it would be continuous on this portion of the real numbers. How about x minus 1, quantity squared? Again, polynomial. So it would be continuous there. So the only place this function could be discontinuous would be at the juncture point. Okay? So let's see, if I put 1 in here, 1 minus 1 is 0, 0 cubed is 0. So my output would be 0. What if I put 1 in down here? What if I could use it? Okay, if I put 1 in, do I get 0 again? So the whole caused here would be filled with that one up there. Okay, so that's continuity, but we know it can be continuous without being differentiable. So let's think about differentiability.